Hello. In this video, we're going to cover how to troubleshoot TLS. We're first going to introduce what TLS is, and then we'll move into a couple different failure scenarios and how we can troubleshoot them and resolve them. We're not going to go into a technical deep dive of what TLS is and how it works in terms of a TLS handshake, encryption, and the PKI public key infrastructure model. So let's go ahead and dive right in. So what is TLS? Well, TLS stands for Transport Layer Security, and at a very high level, all TLS really is applying encryption to your transport layer TCP packets. If you recall, the transport layer is layer 4 of the OSI model, so TLS essentially is applying encryption to that layer. If you've used a website before that has the prefix https:// and you saw maybe a green lock in your address bar, then odds are you were using TLS. Now, keep in mind, HTTP operates at layer 7 and TLS operates at layer 4, so HTTP uses TLS to secure its connections. So what connections? Well, at one end you have a client, and that's usually your web browser, and it connects to a server on the internet, such as duckduckgo.com or some other server. Well, the client and the server, they have TLS certificates that they exchange and they compare, and they create what's called a chain of trust. If all TLS certificates in that chain of trust are there, the chain of trust is considered complete and the TLS connection is verified and allowed to proceed. So what does a chain of trust look like? Well, this diagram shows it pretty accurately. A chain of trust consists of three elements, well, at least three elements: a root CA certificate, an intermediate CA certificate, and an end entity certificate. So what is a root CA exactly? Well, a root CA is some sort of entity that is responsible for issuing TLS certificates for other entities. If you use services such as Let's Encrypt or DigiCert before, then you've used a root certificate authority. That root certificate authority usually creates what's called an intermediate certificate authority. And that intermediate certificate authority does the same thing. It issues certificates for other entities. What entities? Well, an end entity such as your web server or your web service. So if you were a customer and you wanted to secure your website with TLS, you would reach out to some intermediate CA cert, and you will get your own end entity cert to secure your website or your web service. Now, at the bottom, we see two end entity certificates, one for app 01 and one for app 02. That's just illustrating that a given intermediate CA can sign and issue multiple TLS certificates for multiple different users. You'll also notice that the intermediate CA is in a dashed box. Well, that is because the intermediate CA is not strictly required. We could instead get our certificates directly from the root CA, but that's not really a common thing, so I just kind of wanted to mention it for completeness, but kind of gloss over it for now. In this specific video, we're going to stick to this architecture where we have a 3-layer or 3-level chain of trust, starting at the root and going all the way down to the end entity. So we can have 3 elements: the root CA, the intermediate CA, and the end entity. And this is the model that we're going to focus on in this particular video. Now, we talked before about how the client makes a request to the server, they have TLS certificates, they make a chain of trust, but where are these TLS certificates and who has what? Well, the client usually has the root certificate authority certificates in what's called its certificate authority bundle, or CA bundle. Every client, every operating system, Windows, Mac OS, Linux, every operating system comes installed with a certificate authority bundle, a CA bundle, by default. That CA bundle contains all of the publicly trusted root certificate authorities: Let's Encrypt, DigiCert, Amazon, maybe Google, all of those. And when you update your operating system, that bundle may get updated as well. So we know the client has the root CA certificates, and it's basically just a concatenated file of all of the TLS certificates for all of the root CAs. So the server presents the rest. The server will present the intermediate CA and the end entity certificate to the client on each TLS connection. Together, the TLS certificates from the client and the TLS certificates presented by the server, they form the chain of trust. And if all of those certificates are valid and they form that chain of trust correctly, the TLS connection is considered verified and it is allowed to proceed. But the client doesn't really need to only have the root certificate authority. The client could actually have the root certificate authority and the intermediate certificate authority certificates in its CA bundle. It's not strictly required for the client just to have the root. It can have the intermediates as well. In this particular case, the server would present its end entity certificate, and together the client and the server will create a chain of trust. But this time the client has 2 certificates and the server only presented 1. Now this model is not too common, so we're not going to focus on it. We're really going to focus on the prior model where the client has the root CA and the server presents both the intermediate and the end entity certificates, and they create that chain of trust and you have a verified TLS connection. So let's see what happens when one of these certificates are not there. Well, let's say the client doesn't have the root CA for a given TLS connection. So what's going to happen? The client will connect to a server. The server will respond and say, hey, here's my intermediate and end entity certificates. Client says, oh, well, I don't have the root certificate authority for those certificates. The connection is not verified and it is dropped. Same thing if the server doesn't have the intermediate CA cert. Well, same thing. The client makes a connection. The server presents its end entity cert. The client has the root cert, but there's no intermediate cert in between to link them together. So the chain of trust is not created and the TLS connection is not validated or not verified, and it does not proceed and it is dropped. Same thing if the server does not have the end entity cert. The client will make a connection. The server will respond with the intermediate cert. The client has the root. It says, hey, that's great. I have the root. I now have the intermediate, but where's the end entity? The chain of trust is not completed. It is not verified, and the TLS connection is dropped. So for the rest of this video, we are going to focus on connections that have this type of architecture where the client has the root CA cert imported and the server is presenting the intermediate and end entity cert from itself, and then they all combine to create the chain of trust. So this is the happy architecture that we're going to strive for in the rest of this video. Granted, we're going to see some failure scenarios where something in this diagram is missing, and we're going to kind of have to troubleshoot what's going on. But before we do that, what do these files actually look like? So we know that there are files on the client, there are files on the server, but what do they look like? Well, TLS certificates can be encoded in a variety of different formats, but the most popular format, at least for the Linux side and Linux users, is the PEM encoded format, or privacy enhanced mail. So all PEM encoding means is you take the TLS certificate and you base64 encode it and you put it in between these begin and end certificate tags. And you do that for the root, for the intermediate, and the end entity. So if you're looking at this graph, you have the root certificate is on the top, the middle is the intermediate certificate, and the bottom is the end entity certificate. And if you look a little closely, the contents are actually different between them because the certificates are different. So if you look here, the contents are actually different. And these contents were taken from the duckduckgo.com web service. Okay, so when you're dealing with TLS certificates, you might come across a term called full chain file. What does that really mean? If you've ever used Let's Encrypt before, you might have seen a file called fullchain.pem. And that file, all that means is a full chain file is the concatenation of the end entity certificate and all intermediate certificates up to, but not including, the root CA certificate. So in our particular case, a full chain file might look like this, where you have the end entity and the intermediate certificate concatenated together into one file. And keep in mind, we do not have the root CA cert in this file. Okay, great. With that being said, let's take a look at how we can find information about our TLS connections and kind of troubleshoot things. So I'm going to go ahead and open up a private window. I'm going to navigate to a server that I've created called tls01.matthewsanabria.dev, and we're going to go to this website. Great, our Firefox web browser connected. We see the HTML output here, TLS01. We see the lock. If we click the lock, we see connection secure. Let's click more the arrow. click more information, and view certificate. So let's get information about this connection, because so far it looks like Firefox successfully connected, right? So we see here on the very top 3 tabs, and from left to right, those tabs represent the end entity certificate, the intermediate certificate, and the root certificate. Let's take a look at the end entity certificate first. So here we're going to see a bunch of different sections and fields. What are these sections and fields? Well, given that PEM encoded content, this is just a decoded version of it that you can see. So let's focus on some of the fields here that we care about. So under the subject section, we see a field called common name, or otherwise known as CN. The CN field is the name that this certificate is valid for. So since our CN is tls01.matthewsanabria.dev, that means this TLS certificate is only valid for tls01.matthewsanabria.dev. The next section is the issuer name, and you can see fields such as country, organization, and common name. This just tells us who issued this particular end entity certificate. Well, that's easy. A certificate with the CN of Let's Encrypt Authority X3 issued this end entity certificate. The next section is the validity. This just tells us when the certificate is valid. So this particular TLS certificate is not valid before April 12th, and it is not valid after July 11th. So if you try to access the web service with this particular certificate after and before those times, you will get an error. So the web server administrator for this particular web server, which is me, would have to rotate the certificate before July 11th in order to maintain proper TLS connections. The next section is subject alternative names, or SANs. The SANs field is just a list of DNS names or IP addresses that are also valid for this particular certificate. A common use for this is to have one single TLS certificate be valid for more than one domain or subdomain. So for example, if you had a TLS certificate that was valid for www.example.com, you might want to include a subject alternative name called example.com. That way your TLS certificate is valid for both www. And just example.com by itself. That's a very common scenario there. Scrolling down, the last field that we actually care about here is the download field, and if we click it, we can see this particular end entity certificate in PEM format, and that is the content there. Not much to see there, but I just wanted to show that. Okay, great. So let's follow the chain. So we know that the issuer was this common name, and this is a link. So let's click it. It brings us to the second tab. That means the TLS, this end entity certificate, was issued by this certificate, which we also have. And then this intermediate certificate was in turn issued by this root certificate, which we also have. And then this root certificate was issued by itself. Well, that's kind of how root CAs work, right? I mean, if you apply to be a root CA like Let's Encrypt did or DigiCert did, you essentially create your own certificate and you build up a trust model for it. And that's kind of how the root CAs work at a basic level. Eventually, when you complete the process to become a root CA, your certificate will be publicly trusted by all of these major operating systems, and it'll be placed into the bundle for the operating system. Okay, so we saw how Firefox gave us the information, but let's look at a CLI. So I have a Windows subsystem for Linux, and I have a Debian Linux, installed here. So we're going to look at some commands that we can use to gather the information that Firefox was already showing us before. The first command I'm going to show you is called the curl command. So curl is just a command that's used to make web requests to a web server. This command operates at layer 7 because it speaks the HTTP protocol. So we're going to do curl-v. So v stands for verbose, give me more information. And we're going to connect to https://tls01.matthewsanabria.dev. We hit enter. You could ignore all of this expire output. The very first line that we actually care about is the first one right here, trying IP address. So when you type curl and you give it a host name to connect to, the very first thing it does is a DNS lookup to resolve that host name into an IP address. Once it has that IP address, it connects to that IP address, and the next thing that we see that we care about is this CA file and CA path parameters. So what does that mean? Well, curl, the CA file parameter means the file that curl is using as its root CA bundle, right? Because curl is now our client. Clients have CA bundles. So this particular parameter says, hey, I'm using this particular file as my CA bundle. It's set to none, which means curl is not using a file. But right beneath it, we see CA path. CA path is the same concept. Which directory do you want to use as your CA bundle? And when you use a directory, that just means that every file in that directory is included in your bundle. So no need to concatenate them into one giant file. You can just have separate files. So we're going to take a look at this Etsy SSL certs bundle path in a minute, but this is where curl is getting its CA bundle from, this directory. Then we can see a TLS handshake was performed. We're not going to get into what a TLS handshake is and how it works, so we'll skip that. The next thing that we care about is the server certificate parameter, and it has all of this information. If you look closely, this information matches up with what Firefox is showing us over here. So if we go back to the end entity cert for a second, we'll see that the subject matches the subject, the start date and end date match the validity, the subject alternative name matches the SAN over here, the issuer matches the issuer, and the SSL certificate or the TLS certificate was verified successfully. So curl reached out to the server responded, and curl says, oh, I was able to create that chain of trust. You are a verified connection. I will proceed. So once curl passes the TLS part, it goes on to the HTTP part. It makes the HTTP request, which we're not going to cover because this is not an HTTP video. And then it receives the raw HTML content as a response, which we can see the rendered version in our web browser. So these are the same. So we've just did the same action in Firefox that we did in curl, vice versa. Okay, let's look at the next command. And we're going to come back to the Etsy SSL certs in a minute, but I want to look at the next command first. The next command is called OpenSSL, and this command operates at layer 4 now. So it doesn't speak HTTP, it speaks TCP only. So let's do OpenSSL, and we're going to use the s_client command, or the subcommand. We're going to use the show certs option, and we're going to connect to a host. So which host? tls01.matthewsanabria.dev, and we need to give it a port because we're not speaking HTTP anymore, we're speaking raw TCP. So TCP wants a host name and a port. We give it port 443 because that's the default HTTPS port that my web server is listening on that knows how to communicate via TLS. Okay, once we type all that in, we hit enter. Oops, sorry, my Windows subsystem for Linux just froze there for a second, so I'll just remake that call. Okay, once we hit enter, we'll see the first line says connected. We've connected to that remote host, and now we can see all this information. So the first couple lines just show us the chain of trust, but I kind of ignore that a lot because it's not always useful. What I kind of focus on instead are these certificates. So you'll see the next thing is these 3 little dashes, and you'll see them at the bottom here too. In between these 3 little dashes, so all of this content that I'm highlighting, in between those 3 dashes are all of the certificates that the server has presented to you, the client. So let's kind of go line by line. Well, we see the chain that it presented us. The very first certificate that the server presented us was this one, number 0. The S stands for the subject. The subject contains a CN of TLS01. This is all matching what Firefox is showing us. This particular end entity certificate was issued by this intermediate certificate, and here is the raw PEM content. If we look at the PEM content from Firefox again, real quick, we'll see that these match up rather nicely. Ends with 6VXS and 6VXS. So this is the same certificate. Let's keep going. The next certificate that we got was this one right here. This has a subject of the country of US, the organization of Let's Encrypt, the CN of Let's Encrypt Authority. That matches up here. The country of US, organization Let's Encrypt, and the common name was Let's Encrypt Authority. And this particular certificate was issued by the DST root. So if we go ahead and click into the intermediate certificate, we can see that it was issued by the DST root. Same thing with the PEM contents. This PEM content would be the same if I were to download it from the Firefox side. Scrolling down, we're going to ignore a lot of this output here because really all we care about right now is the verification. So we're going to go down here to verify return code. This verify return code means whether or not our TLS connection was considered verified. A return code of 0 means success, and you can see that with the parentheses, and it says OK. So we can tell that OpenSSL was able to successfully make a TLS handshake with this particular endpoint. So the chain of trust was complete, and the TLS connection proceeded. Okay, great. So we know all of the information. We're able to get the information from Firefox and from the CLI. Let's take a look at the Etsy SSL certs that I showed you before in the curl output. If I scroll up, remember when I said the CA path was Etsy SSL certs? Let's just ls that location. So ls Etsy SSL certs, and you can see, whoa, there's a bunch of files in here, bunch of files. All of these files are individual root CA certificates, and they all get concatenated and they get thrown into this file right here, cacertificates.crt. Now, different versions of Linux or different distros of Linux put this file in a different location or a different name, but this is what I'm talking about for Debian. So if we look at this file, if we cat it out, we're just going to tail out the last 100 lines of Etsy SSL certs CA certificates.crt. We can see that it's a concatenation of all of these files. Okay, great. But now we have some more information. We know that when we connected to TLS01, that the server responded with 2 certificates, and my client should have the root to make up that chain of trust. So where's the root? Well, it's in here, Etsy SSL certs. But which root is it? Well, we know it's the DST root CA x3. So maybe let's look for that here. We see DST root CA x3.pem. Maybe that's the file. Well, let's download it from Firefox. So now we have, this is the root pem right here. And let's cat out this file right here. So cat Etsy SSL certs and then DST root CAX3. We'll cat it out. And if we look at them side by side, well, those are the same. It ends with CNTUQ, CNTUQ. So that's where curl and OpenSSL were able to read the CA bundle and make that valid TLS request. What about Firefox? We know that the server is only returning these 2. How did Firefox know to find this third one? Well, if we go to Options and then Privacy and Security and scroll all the way down to Certificates, we can view certificates. If we click in here and start searching for DST, we can see that Firefox has DST root CA already imported in its own CA bundle. And that's how Firefox was able to trust this connection and complete the chain of trust. Okay, so that's what a TLS connection looks like when everything's working successfully. What about when we have a failure? So I have another web server up called tls02.matthewsanabria.dev. We'll connect to it. Firefox connected successfully, and we see TLS02. But I just said that this was a failure mode, so we're not seeing anything that's failing here, right? Let's click the lock. Let's click the arrow and more information. We'll view the certificate. And we see TLS02, so this is the end entity cert. We see an intermediate, we see a root, everything's looking really good here, right? Okay, great, Firefox looks good, but what about the CLI? Let's try to curl this now. So we'll curl TLS02, and we see the same trying, but we see an error now. We don't see the actual output anymore. The error is certificate problem, unable to get local issuer certificate. So curl wasn't able to connect. What about OpenSSL? So if we connect to OpenSSL on 02 now, well, OpenSSL also returned a verify error, and it says I couldn't verify this connection. But let's scroll to the top of OpenSSL where the connected line is, and we'll go down. So we see in between the 3 dashes, these are all of the certificates that this server presented to me, the client. And I'm noticing that there's only one here. And the certificate that it presented to me was this one right here with the CN of TLS02. So while Firefox has TLS02, the intermediate and the root, my OpenSSL connection only got the end entity cert. It's missing the intermediate cert because I've already proved that the client on Debian has DST root, and I've already shown you that the server has given us the end entity cert for TLS02. What we seem to be missing on the CLI side is this middle certificate, this intermediate cert. And you'd be right for thinking that, because we are. So how do we solve this? Well, we could do one of two things. We could either import this missing intermediate certificate onto the client in the SSL bundle or in the CA bundle, but that's a little bit too much work. The web server itself should be responsible for presenting all the necessary certificates. So let me put my web server hat on, and I'm going to SSH into TLS02 and maybe take a look at the website configuration. So I'll drop down to root, and I'm running Nginx for this web server, and it's okay if you don't know anything about Nginx. We're going to kind of cover a little bit about it. So I'm going to look at the Nginx config file for this web server, and I'm seeing that we're using this SSL certificate or TLS certificate and this TLS private key. We're not going to worry about private keys too much because those don't really have anything to do with the chain of trust. The private key is used for encrypting and decrypting the public key and other connections, and that's more for a server side thing, so we're not going to worry about that. What we care about is this SSL certificate. So we're using a certificate located at etc let's encrypt live TLS02 matthewsonberg.dev cert.pem. Okay, fine. But TLS01 worked, and why was that? So let's go in that directory and look. Let's cd into etc let's encrypt live TLS02 and take a look at what's in here. So we see a cert.pem, a chain.pem, a full chain.pem, and a privkey.pem. Let's start catting some of these out. So we'll cat out the cert, and we can see that this particular cert, if we download the one from Firefox, that this cert matches up with the end entity cert. See how they both end with the same Q1DN. Okay, great. Let's cat out the chain now. The chain is this. We don't know what that is yet, but let's look at the one from Firefox because Firefox seems to work, and let's download it real quick. Okay, so this cert matches up the intermediate certificate, so that looks the same. They both end in the same thing. Okay, what about this full chain? Oh, the full chain contains both the client or the end entity cert and the intermediate cert. So it looks like our web server is just misconfigured and it's not presenting us the right file. So let's change it. So instead of presenting just the cert.pem, we're going to present the full chain.pem. We will restart our web server and then exit out of here. And let's try to connect again with curl. And notice this time we connected and the SSL server, the TLS server certificate was verified, and we were able to connect, and this time we got the HTML output. So that was the problem here. This particular failure scenario is simulated when the intermediate certificate is missing. And notice how Firefox didn't have a problem. Why is that? Well, if we go back into the options again, and we go back to privacy and security, scroll all the way down, and view certificates, and look for DST root again, look what's beneath it. Let's encrypt authority x3. That's the intermediate certificate that we were missing. Firefox already had it imported. That's why Firefox didn't have this problem. So it's something to think about when you're setting up and using web services and TLS connections. Depending on the client you're using, you may have to import certain certificates or reconfigure your web server. In our particular case, we reconfigured the web server to present the proper certificates. Okay, let's move on to the next failure scenario, which is tls03.matthewsonabria.dev. This time, Firefox is not happy. We have this big warning. So let's click Advanced, and we will see what the error message is. And Firefox just says websites prove their identity with certificates. Firefox does not trust this site because it uses a certificate that is not valid for tls03.matthewsonabria.dev. The certificate is only valid for app03. Okay, so we connected to TLS03, but we got a certificate for app03. So clearly there's a mismatch there, and Firefox says, nope, this is not verified, I'm dropping this. Okay, what about curl? So let's curl on the left side, and we'll curl 03. And if we look at 03, we see it's trying to go to the IP, great. We scroll down, if we see this SSL connection, okay, server certificate, we see that it's giving us a certificate for app03 instead. If we click Firefox's little lock and click the view certificate like we were doing before, that's lining up. So both Firefox and the CLI are getting a certificate for app03. What about OpenSSL? So we'll connect to 03 this time. Okay, so we'll go up to the connected line. We'll look in between the two the two delimiters, so 3 dashes. So OpenSSL is being presented with 2 certificates, which is lining up with what Firefox is saying. And it's the first certificate is for app03, which is also lining up with Firefox and curl. And the second certificate is the intermediate. Okay, but look at something here at the bottom. The verify return code was okay, but curl couldn't verify because of this error, no alternative subject name. Firefox also had an error, so why is OpenSSL working? Well, it's because of the layers. Firefox and curl both operate at layer 7. They're making an HTTPS request, but OpenSSL is operating at layer 4. It's making a raw TCP request. Given that the server responded with 2 certificates, and I have the third one in my CA bundle, which I proved before, this raw TCP connection at this layer 4 completes a chain of trust. But curl, since it's operating at layer 7, does not complete the chain of trust because of the hostname mismatch. Keep in mind, OpenSSL doesn't care about host names, it only cares about the IP address. And that's why when we connect to this particular host name, it does the DNS lookup and it's really connecting to the IP address instead. And we don't really care about the host name. That's why OpenSSL is showing verify okay. Reason why I show you that is because it may be necessary to use multiple tools to debug a certain problem. So what's going on here? How do we fix this? Well, the simplest scenario is if it's giving us a cert for app03, maybe we should access it over app03. So we need our network administrator or our system admin to create a DNS record for app03 that points to that web server. Luckily, we have that already existing, so we'll just see if that works. So we went to app03 this time and everything works. Okay, but we don't want to have our customers or our clients have to go to app03. We want them to go to TLS03 because that's the domain that we want to use. So what's going on here? Well, let's again log into the web server. So this time I'll SSH into TLS03 because I am putting my web server hat on, my web server administrator hat on, and I'll look at the Nginx configuration for this server. And I'll see the SSL certificate that's being used here is etc let's encrypt live app03.matthewsnobria.dev full chain. But this is using app03. We don't want to use app03. We want to use TLS03. So let's see if one of those files even exists. ls etc let's encrypt live. Okay, TLS03 exists. So let's see if there's anything in there. Okay, there's some certs in there. And it looks okay. So maybe this was a mistake on the web server administrator, and let's try to change it. TLS03, TLS03. We're not going to make the same mistake that we made in 02, and we're going to actually use the full chain this time. So we see that up here. Let's save and quit. And we'll restart Nginx. We'll exit out, and we'll try to just connect with curl. Okay, this time curl worked, and we got some output. What about OpenSSL? Does that still work? Yep, OpenSSL is happy too. What about Firefox back on the TLS03 hostname? Let's refresh this. Oh, Firefox is good now too. If we look at the connection now, view certificate, Firefox is getting the complete chain for the right hostname. So what happened here? What happened here was the web server administrator misconfigured the TLS certificate, and it was presenting you a TLS certificate for a different domain than what you were accessing. This is actually very common, and this is why I included this particular scenario in this video. And the way we fixed it was we actually went back on the web server and reconfigured it to use the correct certificate. Okay, let's look at our third and final failure scenario. So TLS04.matthewsnobria.dev. And again, we see Firefox is already complaining. It's saying, hey, I give you this error, but we're going to click advanced and we're going to read it. Someone could be trying to impersonate the site and you should not continue. Well, that's kind of alarming, so what's going on? Websites prove their identity via certificates. Firefox does not trust TLS04.mscenario.dev because its certificate issuer is unknown, or the certificate is self-signed, or the server is not sending in the correct intermediate certificates. So that's a mouthful. So something's going on here. Let's click the lock and see, what the certificates we're getting is. So we're getting a certificate for TLS04.matthewssanabria.dev, and the intermediate certificate is Matthew Sanabria Intermediate CA. Okay, this is weird. This looks completely different than what we were using before. Well, that's true, because before we were using publicly trusted TLS certificates from Let's Encrypt, but this time we're using an internal self-signed certificate from for our company's internal certificate authority. Companies themselves can stand up their own root CAs and their own intermediate CAs and use them for company traffic. But they won't be trusted publicly because the CA certs, the root CA and the intermediate CA certs, are not on the client side. So what's happening here? We're getting an end entity certificate for TLS04.matthewssanabria.dev issued by this Matthew Sanabria Intermediate CA, and this Matthew Sanabria Intermediate CA is issued by Matthew Sanabria Root CA, but we don't have that anywhere. Where is this? So let's reach out to our system admin who manages this and ask them, like, hey, I'm trying to connect to TLS04.matthewssanabria.dev. I don't have the root CA. Do you have it? But before we do that, let's try to curl, because we always want to, test more than one scenario. So we'll curl. Curl says the same thing. Hey, unable to get local certificate. I have an error. Let's see if OpenSSL can give us some more details here. So we'll go to OpenSSL. Scroll up to the connected line. Look in between the two certificates again, like we always do. And we see two very large certificates in here. The first one is a certificate with a subject name containing the CN of TLS04. And it was issued by Matthew Sanabria Intermediate CA. Okay, so this is matching Firefox right now. The second certificate we got was the Intermediate CA certificate, and the CN is this, which is matching Firefox again, and it was issued by Matthew Sanabria Root CA. Okay, but this is the second time we ran into Matthew Sanabria Root CA, but we don't have that. I don't see that anywhere in my CA bundle. And if we look at OpenSSL, the verify return code is wrong. So if we ls etc ssl certs, we don't see a Matthew root CA anywhere in here, do we? No, we don't. So we need to ask our system admin, like, hey, I want to connect to your TLS04 service and I need a root CA to import. Do you have one? Luckily, our system admin works fast and he gave us this ca.pem for Matthew Sanabria root CA. So we'll go ahead and open up in a notepad and we'll see here's the actual PEM file. So the very first thing we want to do is test this. Let's test it in Firefox. So Firefox has the end entity cert. Firefox also has the intermediate, but we're missing Matthew Sanabria root. So let's tell Firefox to import this. So we'll go back to options, privacy and security, go down to certificates, we'll see this import button, and we're going to import this root CA that my system admin gave me. We'll open it up. It'll say, hey, you are asking to trust the new CA. Do you want to trust Matthew Sanabria root CA for the following purposes? Trust for websites, trust for email. Well, I'm going to trust for websites because we're not dealing with email here, and I'll click OK. Then I will look for this in this little area, and I'll see that Matthew Sanabria root CA is now here. So I like that. I'll click OK. I will go back to TLS04 now, refresh. Okay, Firefox is happy now. If I look at the certificate again, we have the end entity, we have the intermediate, and we have the root CA that we just imported. This chain of trust is complete. Firefox verified it and was able to connect. But what about the CLI? Let's try to curl again. Well, curl's still broken. And what about OpenSSL? OpenSSL still broken because we imported the root CA on Firefox, but we didn't import the root CA on our Debian install. So let's go ahead and do that. So I've already downloaded the root CA here on our Debian install, just for the sake of this video. But if I catted it out, it is the same content that I just copied and pasted into Firefox. But to import a CA certificate into a CA bundle, that differs between Windows and Mac OS and Linux. Specifically for Debian, in order to import it, you would think that you would have to just append it to the CA certificates file, right? And do something like this: cat it out, append it to etc SSL certs CA certificates, and you would think that you would just add it to the end, right? Well, no. In Debian, you can't do that because these certificates are managed in a special way. So what we need to do is we need to copy it to a specific location. So we'll do sudo copy Matthew Sanabria user local share CA certificates, and we want to call it Matthew Sanabria root ca.crt. So why are we changing it from .pem to .crt? Linux doesn't really care about file extensions, so why are we doing this? Well, the program that Debian uses to import CAs into its bundle looks for all files with a .crt extension. That's why we need to do the name change. So we'll go ahead and do the name change, but okay, so we put the CA bundle there, but curl still doesn't work, and neither does OpenSSL. So what's going on here? Well, we now need to tell Debian to use this in its bundle and regenerate its bundle. How do we do that? Well, there's a dpackage command, dpackage reconfigure, and we want to point it to, I'll put this up there, we want to point it to CA certificates. Okay, so this blue screen came up. It says this package may install new CAs when upgrading, yada, yada, yada. Do you want to do this? Yes, I do want to do this. And we'll wait for the output. It says, hey, here are all of the CA certificates in user share CA certificates. But we didn't put our certificate there. We put it in user local share. So we are actually not modifying any of this. We're just going to hit OK. So if we hit OK, oh, another Windows bug there. Windows WSL bug. I'll wait for this to go. Okay, so once we hit OK, we'll see that it says 1 added, 0 removed. Well, but we didn't add it to user share CA certificates. We added it to user local share. That's a special directory to make local changes. But now, if we try the curl again, we'll see the curl works. It was verified OK. Let's try OpenSSL. OpenSSL works. It is now using that new CA certificate in the bundle. Can we prove that? Yes, we can. Let's ls etc SSL certs. And what do we see here? We see that Matthew Sanabria root ca.pem is now included in there. And if we compare it to what Firefox has, so I'll just cat it out, cat etc SSL certs Matthew Sanabria, and we look at them side by side, same thing. The constants are the same, QENG8, QENG8. And now we have successfully imported Matthew Sanabria root CA in Firefox and on our CLI. Okay, that final failure mode was meant to simulate a self-signed certificate trust, and it was meant to show you how to import on the client side now, because failure modes 02 and 03 were dealing on the server side. I wanted to show a failure mode on the client side as well, because it is a common practice to have to import a CA bundle or a CA certificate on the client in order to successfully connect, especially if you're in a corporation where they have their own internal root CAs and intermediate CAs. Okay, with all that being said, thank you for watching this video. I hope you learned something about TLS and how to troubleshoot it. If you have any questions, comments, or concerns, feel free to contact me via one of my contact methods. And thank you for watching this video, and I will hope to see you soon.